seminar is a bit long, it's almost 70 slides, so I will try to be fast, but that's good, let's move on. So IIT, for those that don't know, it's located in, the headquarters of IIT is located in Genova, and we are more than 1,000 researchers, and then we have other partners in other universities that are linked to the base central headquarters. There are 4 lines of research domains, big ones like robotics, nanotechnology, neuroscience, and drug discovery. And my academic career started in 2009, where I joined IIT as a fellow researcher developing a microturbine for power generation. So something not really related to robotics, but it was a kind of starting project to enter in IIT and join the advanced robotics group that started to develop a quadruped robot. First we start with a leg, we were studying some passive compliance at the foot. I was involved in the low-level control, like we need to move the robot, right? And we wanted to move in torque control. So we were implementing a low-level torque control, and then on top of that, an outer loop of impedance control. And we were, I was studying the limitation of the impedance control in real implementation on a real hardware. And then I was visiting Max Planck in Tübingen for a few months, and there I started to implement what is a joint work made with Andrea. It is about all body control. Then became a postdoc and started to do other stuff like moving to locomotion. So locomotion involves different tasks. At the beginning we were involved in reactive locomotion, so implement reflexes and heuristics to be able to adapt to rough terrain. Then we moved on other gates. Other colleagues implemented trot gates, and with my student I was implementing also a bounding gate, which is a kind of gallop with the front leg simultaneously touching on the ground simultaneously. It's not really like a gallop, it's like a different gate. And disturbance observer, which was meant to observe external disturbances and compensate in the controller. Then also was trying stair climbing algorithm and online identification algorithm. Finally, the last 2 years, I was a researcher there, and I was extending the work with Andrea, incorporating acquisition limits in the whole body controller, doing experiments with that, and start to work on planning trajectory optimization with the lower dimensional models, including a certain degree of descriptiveness. I will talk later about this. Actually, we'll do another seminar about these 2 topics, I think, because they are too wide. And I was also working on replanning trajectories in an MPC fashion. Also was studying on soft terrain, locomotion of soft terrain, on foam in this particular case, and implementing a hierarchical body control to be able to control an arm task together with the legs. So for those of you that don't know, our lab is a dynamic leg system lab, and developed many robots, many quadruped robots. We started in 2010 with IQ, the first version of IQ robot. Then we did a copy of IQ, which is the one we bring here in Trento, and we will use with Andrea. It's called IQ Blue because it's blue. And then we did another version of IQ, which is able to self-write, which is called IQ2 Max. Then a mini version, which is like kind of like Cheetah Mini robot, and an arm, an hydraulic arm, and that we merged together with a quadruped platform, and we called IQ Center. And then in the end, the last robot, which is IQ Real, that it was presented in April this year, after 3 years of development. This is the structure of my talk. After a first motivation part, I will talk about the model identification quickly to understand how did we identify the most relevant part of our model, which is the center of mass of the trunk, by the way. I will anticipate. And then we will move to trunk stabilization. So this is a strong connection with the course that Andrea just gave. Then I will tell you about some strategies for locomotion on rough terrain. So we move out from the assumption of flat terrain. Many labs do it. We are interested in different kind of environment where rocks are falling, rocks are moving, there are degrees, there are steps, there are stairs, there are ramps. And for addressing this, a very effective way is reactive locomotion. Then vision-based locomotion, it means using the visual feedback for locomotion. And then we extend this, adding an optimization-based planning ideas that allows us to push the limit and the boundary of the performance of the robot. And then I will introduce a very, very new concept that we are working on, that is the one we use to do the IQ Real demo, that was consisting in pulling a plane of 3 tons. You will see a video afterwards. So at the beginning, why legged robot instead of wheel vehicles? Because legs allows animals and humans to traverse terrain that are complex, are unstructured, and also trucks can be stuck in mud on ground of this type. Most important, they are versatile. So legged robots allow us to address the different kind of terrains. Another point is that legged robotics, it's very multidisciplinary. So there are many subjects involved in this study. In this, we have mechanics for the design part, electronics that allows us to transfer information from the sensors, from different kinds of sensors, synchronize them. And we have hydraulics, because I didn't tell you, but our hydraulic robots. So we have a very high power to weight density, and this is super important to do dynamic motion, because if you use electric motors, you will, to have the same power, you will need a big motors, or use high gear ratio. And the problem with this is that you need to carry, the robot itself should carry its own weight, so the weight increases. So hydraulics is a good compromise for this. On top of this, hydraulics has some inherent passive compliance in the oil compressibility, due to the oil compressibility, so it's very good to deal with impact that are the order of the day in legged locomotion. Then you have control, as I said, planning, state estimation, a very important field that is needed to understand to make the robot understand how it's moving in the space. So reconstruct the linear velocity and the linear positions. We have computer science, image processing for the vision feedback, that we need to be able to acquire and on the fly online the map of the environment, so be able to merge the frames that come from the vision sensor, that can be a LiDAR, an RGB camera. It can be both of them. They can be fused together and synchronized, and of course machine learning. And we have some also other topics like model identification, filtering, signal conditioning. This is a summary of the early year of development of IQ. You can see here it's climbing stairs in a pre-planned way. Here is selecting footholds to emulate crossing a river, and it's quite robust. You see that the researcher Ioannis removed one rock, and there is a reaching motion that is able to achieve a stable foothold anyway. We have a very early vision feedback in these years with a stair camera, and we were using that to acquire the map of the terrain. In this example, the robot is trotting, completely blind. There is just an IMU, and we have a torque sensor at the joint that allows us to estimate the ground action forces, so detect when an impact is happening with the terrain and adapt the trajectory accordingly. We see here how the IMU is able to measure orientation and acceleration and angular velocities in order to take sideways steps, for example. This is Victor Barsual that did the same task, but it was not as good. This is a flying trot. It's a very, very important milestone because the robot is having 4 legs on the air and is able to. And thanks to torque control and impedance control, we are able to create some emulate stiffness at the feet in a way that we are able to dump and accommodate the impact forces. This is a reflex task. I will talk later to address when you are in a foggy or there is no vision, and it's able to at least cover. This is a squat jump. And here the concept I told you, we were able to, thanks to very, very high bandwidth torque control, we reach up to 40 Hertz in bandwidth in this prototype. We are able to emulate any kind of stiffness, not any kind of, but we are able to emulate a virtual spring between the ankle and the foot, and change the stiffness online. And this is a comparison with the real spring. Finally, this is the work of Andrea, and we were climbing in this V-shaped wall between V-shaped work. We had to optimize ground action forces in order to be in the middle of the cone in order not to slip. This is very important. Then more recent results are related to deal with very rough terrain locomotion. So this is an example of the trot, and in here we use a neural network to select the foothold and avoid the gaps. Model-based control, and to perform optimization of trajectory, we need a good model of the robot. So the first thing we did was to try to identify the model of the robot as good as possible. So first we need to identify between constant payload changes, because the robot, for example, we would like to add the backpack on the robot, a different set of cameras, and these are different from time-varying disturbances like force, wind, pushes, or a cart that is attached to the back of the robot. In this case, we should use identification techniques, while in the other case, we use disturbance observer. I will talk only about this for the sake of brevity. This was the idea is that if you have the center of mass wrongly estimated, there is an error in the center of mass position. This affects locomotion stability because the ZMP goes out of the support polygon we are planning. We think that online identification techniques are useful for the parts of the robot that can change. For example, a backpack that we put on the trunk, or different set of cameras. While off-align identifications, like using some trajectories, random trajectories to move the legs, are useful for the leg parameters that are never changing. The goal of the online identification technique is to promptly detect a payload change and reflect this change in the model, in the COM estimation, in order that the inverse dynamics controller can be taking into account of this change. And the key idea is also where I work with Andrea. It's to move the estimate we have of the center of mass in order to explain the ground action forces. So we move the estimate we do, and until we find an equilibrium of the moment of the ground action forces. So we should do this when in static conditions. So we have gravity and constant forces, we have no accelerations, and since gravity it's applied on the COM has no moment, and we have only the moments of the ground direction forces that should be equalized. If we define the vector between the central mass to the feet as the difference between the vector between the base origin and the foot, and the vector between the position that represent the position of the COM in the base frame, we can write this, and we can split the two terms, put this one on the right hand side, and using the distributive property of a cross product, we can put the sum inside, and using the swapping the terms and using the skew symmetric operator related to the cross product, we can basically find a way to estimate the COM given the ground direction forces. We could do in one step this operation, but what's the problem? The problem is that the estimation of the forces can be noisy. There are compliances, so it's good. We found a good way to use an update rule that continuously recompute these values and updates with gradually approximating to moving the estimate to the real value. And this approach, it works fine. The only problem is that requires accurate force sensing. So if we have a foot sensor and it's accurate, it's okay. If you have only torque sensors like we do, we need to estimate the ground direction forces through the leg model, and if the leg model is wrong, then we can have errors. We can also have errors if you have torque offset in our torque sensors. They will result in an accurate force sensing and ground direction forces, so an accurate estimation of the COM. And the other limitation is that it's only able to identify the X and Y component because the skew symmetric matrix here is not full rank, it's only rank 2. And this can be seen as whenever you sum up the ground direction forces, you get basically in static condition the gravity term. And this is, if you do a cross product, the that component has no influence. So in essence, it will not affect. We cannot reconstruct the Z component from the right hand side, basically. This is a simulation of what's going on. We saw that the central mass. Sorry, maybe it was too fast. This was initial estimation, and it converges to the real one. Then I will move to the topic of trunk stabilization. So once we have the model, we can implement a whole body controller. This was the next step we did to be able to find out what are the joint torques that achieve trunk stabilization. So we are, it's a bit noisy, it's hydraulics, it's a pump, an external pump, and to optimize the ground direction forces. So we see on the right side what's happening if we don't optimize for ground direction forces. The robot horribly falls. And the third goal of a trunk controller is also to control the central mass. We see here on the left, in this case, an example where the trunk controller is off. There is only gravity compensation. There is no damping of the COM. And while on the right hand side, the disturbance coming from the arm is damped, and the ground direction forces are swinging back and forth to compensate and keep it stable. Recently we were adding an arm to IQ, another one, because we have another project which is with Inhale, and the goal is to create a center that is able to do search and rescue operations, so opening door, cutting door, drill an anchor to collaborate with firefighters basically, and also removing debris. So inside this email project, we need to be able to teleoperate from far away the arm of the robot. So we need to teleoperate the robot, giving high-level commands with a joypad. So we say go forward, go left, rotate, and approach the door, let's say. And then we want to command the arm and the effector to cut, for example, with a grinder, cut the door or open the door. And we should be able to change, replace the tool. So we can have, at the end effector of the arm, we can have a hand, or we can have a driller, or a grinder, another tool. And we should be able to replace the tools. The arm should be powerful enough to manipulate the object on the environment, so be able to remove debris. And what is interesting for me at least is the workspace augmentation. So moving the orientation of the base of the robot, we are able to increase the workspace of the arm, because we can reach lower points, and we can improve the dexterity of the arm as well. So for this reason, we have an arm task, and we have the trunk task. We have conflicting tasks. We have tasks that can be conflicting. So we are thinking, as Andrea was teaching you in the class, to hierarchical approach, a hierarchical task-based inverse dynamics. And I will quickly recall you what are the tasks that are important to do such motions. And we have the swing foot task that tells us, for example, how what is the trajectory of the swing, and how they are synchronized depending on which gait we have. So if you have a crawl, for example, or a walk gait, we will move 1 foot at a time, and the other 3 will remain on the ground. If you have a trot, we will move the diagonal foot and in sequence, and so we will change the stance condition at a certain frequency. The stance task, as usual, is defined to have a reference acceleration to be 0. So in this case, we are tracking a trajectory which is defined, let's say, in the Cartesian space. Here we say just that the acceleration of the foot should be 0. And this is what it goes in the cost function, because as in Andrea case, we are optimizing. No, different from Andrea case. We are optimizing from joint acceleration. These are floating based joint acceleration. No, the notation is not very accurate. Then we have a trunk orientation task. So this is Jacobian that is related to orientation of the robot, and this is just the orientation error computed from quaternions. And we have the postural task that is trying to keep the robot in a default posture, which is the typical horizontal posture. And we will see that it's very important in our case, because we completely remove the COM task. So as constraints, we have the dynamics that should be respected. So it's defining the relationship between the joint acceleration and the contact forces. We have linearized friction cones. So as Andrea told you, these are the unilaterality contact constraints. That means that the feet can only push and not pull. So we have a vertical force in the normal direction. And also these are pyramidal approximation of the friction cone. So we have a cone that is approximated by 4 hard planes, and mu is the friction coefficient. Then we have acceleration limits, the final one. And if we write the problem, this is a notation that we introduced. We introduced this operator, plus operator, that it represents a soft hierarchy. So it's like summing up with some weights the cost function on the same level without with weights. So it's a kind of what Andrea is doing. While this is the hard hierarchy, which is solving the lower priority task in the null space of the solution of the higher one. So the lower priority task will never violate causable tracking error on the higher priority task. So we'll do the best that it can do without affecting the higher level tasks. While this will have to compromise each other with the weights. So, and this is the dynamic constraint, friction cones, and acceleration limits that are hard constraints. So this goes in the cost function, these are the hard constraints. The nice idea we got is to completely remove the center of mass task. Why? Because the center of mass task requires the notion of the position and the motion of the center of task in the world frame, in an inertial frame. And this requires state estimation. State estimation can be drifting a long time, can create problem errors. So we think, why don't we remove it completely, and we use the postural task to take care of the motion of the trunk. So the idea is that first we take a step, for example, in the direction we want to move, and then the postural task, which is trying to keep the robot in the default configuration, will drive, will resolve the undeterminacy of the COM position, trying to bring the base to follow the feet, and does this like elastic strings. If you have elastics that are pulling the base to the feet, so the feet are rotating sideways, the base will move, and this allows us to have what we really want in locomotion, which is a nice kinematic configuration. So we don't want the robot to really moving in a very weird situation, like configuration where it creates a lot of requires a lot of torque in the joints to move, but we want to behave nicely in a kinematic way. So this is an example done with animal. This is just to show that the approach is cross-platform, so it works for whatever quadruped robot. We have a sideway walk, and we are moving the trunk. This is a trunk task, and having some pitch and roll orientation. And we also moving the height. So we said we don't set any task for the COM position, horizontal position, but we can change the height, and at the same time change orientation at will, and also compensate disturbances. So what's next? In terms of trunk controller, we always did the assumption that the acceleration of the feet is zero, right? Because the terrain is rigid. We do the rigid assumption for the terrain. A study we did with another of my students is called Shamel Fahmy, is to relax this assumption and introduce the contact dynamics in the formulation of the optimization problem. And this allows us to move this constraint and add a term which represents the epsilon, which represents the leg penetration, the foot penetration in the terrain, and we use a contact model like a spring mass model to link to the ground action forces. We don't measure the contact penetration. We just use as an optimization variable because it would be very, very dangerous, because to measure the contact penetration is very difficult. You need to rely on the state estimation, because you touch down, then you need to know from the state estimation how much would you penetrate the terrain, and it's very inaccurate. So for now, the approach was to have a terrain compliance estimator
So we had an external motion capture system that tells us the exact position of the robot, a ground truth of the position of the robot. From that, with forward kinematics, we get the exact location of the foot, and from that we can know in the terrain size, the foam, the size that the robot was working on a foam, we can detect the exact penetration. From the exact penetration, we can estimate the compliance online and feedback into the trunk controller and close the loop. So this is a very early experiment where the robot is working with the feet, each leg separately on a different terrain and estimating the compliance. And here we show a transition between the deformable terrain like a foam, I think it's 2000 Newton or meter stiffness, and then there is a transition to a semi-rigid part which is represented by these tiles, and then moving on to the rigid terrain pallet. And the robot is able to transition between these two kind of terrain. Then we will move to the third part of the presentation, which regards the locomotion strategy. So now we have a successful way to stabilize the base, stabilize the trunk, and we want to track trajectories for the center of mass. We want to track trajectories for the feet, and we need to generate these trajectories. So what we understood from our experience in working with the real robot, because we are not just doing simulation, we learn a lot from actual experiments on the machine, is that it's important to have at the bottom a blind locomotion layer, a layer that is always working. In the worst case situation, whenever there is no vision feedback, whenever rock are falling under the feet, so whenever your environment is changing, it's good to have a locomotion layer that is blind. Then, according to the quality of the visual feedback that you have, you might want to use it, for example, to correct the foot location, decide where to step, or do a full-blown optimization based on the map. I will describe first this blind locomotion layer, and one of the characteristics is that a blind locomotion layer has reactive strategies. These reactive strategies allow us to deal with unpredicted situations. Like you see here on the upper part, the robot doesn't see the step and falls. While here it detects with a frontal force impact and trigger an elevation that so modifies the trajectory in a smart way in order to achieve a stable foothold. The other strategy we have, a reactive strategy, is the push recovery. Push recovery, it's detecting some accelerations, linear acceleration on the base, and is using an inverted pendulum model, taking a lateral step to recover stability. And here the boxing bag was 23 kilograms, so quite important. The whole robot is 92 kilograms. For what regards the heuristics for locomotion, when we go to rough terrain from the lab, we move out, or when we are going on a forest or on rocks, we need a certain adaptation mechanism, an adaptation strategy to adapt to the terrain. The trajectory needs to take into account the shape of the terrain. And this I summarized in 4 points that are very important. That is, the first one is to adapt the trunk orientation to the terrain inclination. So if you think about having a ramp, and we keep the base horizontal, we see that the back legs are extending a lot, and the front legs are contracting, retracting a lot. And this what is the problem of this? Is that these legs are very close to the kinematic limits, and also this one can be close to the workspace, no? Because there's a certain range of motion. So a good way is to match the inclination of the terrain with of the trunk with the inclination of the terrain. For this, we need a terrain estimation, or we rely on the vision system to give us the inclination of the terrain. And the other point is the robot-centric foothold selection. So if we, the first time me and Andrea implemented the crawl on the chimney, on the horizontal chimney, they say, we were finding that the robot was after a certain point like stretching. No, it was taking steps and completely stretched. So it was like, or completely crouching. So it was very bad in terms of locomotion. And this was because we were taking the step, the next step, with respect to the previous foot location. And I will tell you that we should take the step with respect to the base, to the position of the hip. This way you avoid error accumulation. The other point is the haptic touchdown and then online replanning. So as I said, for adapting the trunk orientation, we need to estimate the terrain, and we estimate online the terrain fitting a plane through the stem speed. And then after each step, we adapt the inclination of the base to this plane. For the foothold selection, so if we take a step about not about the actual foothold, but about the position of the hip, we are able to don't accumulate errors. This is super important. And so if let's say my foot is here, and the requirement of the velocity from the user tell us that the step length should be 0.2 meter, so we compute the step 0.2 meters from here, and then whenever we generate the swing, we add this part, this segment, such that we go there. So we either if the foot is too far away or too back, then we are able to always move about the real base position. The haptic touchdown, it's another important concept, and it allows to whenever there is a swing and the touchdown is we need to find the moment in which the real touchdown occurs. And so let's say we have a terrain plane that approximates the terrain. We swing trajectory aligned with this terrain plane, and then at some point we detect the force, the contact force due to the touchdown. And what happens if the terrain is a little bit lower and we don't detect anything? So we should continue to extend the swing to have a reaching motion until you really achieve the contact. Or conversely, we could have a premature touchdown. Could be a rock here and the foot touchdown before. Then we don't have to keep going with the swing. We need to stop. Otherwise, you introduce destabilizing forces on the base, and this is very important. And of course, to avoid the false positives, we check once the touchdown in the swing down phase. We don't. Otherwise, we have chattering. While in the lift off, we recover the synchronism because the lift off is commanded by the planner. So touchdown, haptic, lift off from the planner. And the online replanning, it's a way to recover from tracking errors that can be due to disturbances, delays, model uncertainties, because we define our trajectory with a lower dimensional model, but then with respect to the real model of the robot. we create trajectories that are different. And so after a while, let's say we need to check what is the real position of the feet and create correct the trajectory. We see here in this example all these tools applied. Here the robot is working on a ramp. Then we have a reaching motion, the premature touchdown there, and here you see the foot was on one of the rock, here as well, and then here it was falling, creating a pitch error and recovering in the next step, thanks to the replanning feature. Then if you have a vision available, let's say you have a stereo camera, you have a RGBD sensor, or you have a laser sensor like a LiDAR, you can estimate the map of the environment. So for each step, you first compute the heuristic foothold trajectory that encodes the user speed. So the speed set by the user is to take steps of 20 centimeters to go a half meter per second. And then you evaluate the height map in that point and you correct the swing in order to end up in the real point. And this is, you see here, it's the predicted foothold. It's in red, and the blue is visible. Then the last part, the fourth part of the presentation is about optimization. Why do we want to do optimization for planning trajectory? Because optimization allows us to, knowing the model of the robot, allows us to predict what will be the future behavior of the robot and take actions in advance to have some, to push the limits. So if I know that the robot will have to climb on a step, the robot should start to pitch up earlier enough such that when it arrives at the moment to put the foot on the step, it will not be flat, but it will be already a little bit inclined, for example. And the replanning feature, as I said, it allows us to recover from planning error due to different in the terrain impacts, external impacts, the fact that we are using a simplified model to create the trajectory. And also allows us to accommodate for the velocity set point set by the user. The user is a joypad, for example, in our case, and move the Gibbs command, high-level command of velocity, like go forward, rotate in place, go lateral at certain speed, and the controller should be able to adapt this set point that are non-constant. And what are the problems with optimization? The prediction of behavior has a certain horizon, and the horizon should be large enough, as I said, to have enough in order to achieve enough anticipated behavior. So if you have an horizon of 0.2 seconds and we want to step on a pallet, maybe it's not enough. Maybe you need 1 second, you need 2 seconds. On the other hand, we have a replanning frequency. The replanning frequency should be high enough to, as I said, mitigate for these errors. So if the desired trajectory and the actual trajectory they diverge too much, and the controller can do his best, but if I push from external the robot with a stick, the robot will position will be diverging from the planned one, and maybe the controller is not able to counteract these big errors. In this case, we need to replan. We need to replan in a frequent way. Also, the density of discretization of the trajectory that, as Andrea taught in the course, can be discretized in a coarse way than the controller. So the control loop, let's say it's 1 millisecond or 4 milliseconds, and the trajectory can be 40 milliseconds. So it's we have a problem that is smaller, because the problem, bigger horizon and dense trajectory, creates a an increase in the size of the problem, and so it can be computationally intensive, and we cannot carry out optimization online. So we need to find a way, some kind of trade-off between accuracy and computation time. So in this implementation, first implementation we did on MPC, in our lab, we were extending the work of Pierce Weber to quadrupeds. So we used the linear invariant pendulum dynamics to predict the motion. We use a condensed QP form, so we kind of we did single shooting. We had only the control inputs in the as optimization variable. That in this case are the jerk, it could be the accelerations, could be the ZMP, and we predict the trajectory recursively. We compute the cost function, which was minimizing the jerk, let's say. And as a constraint, we were predicting the future set of footholds, let's say 8 steps or 4 steps in advance, and compute the support polygon, because to keep stability, the ZMP should always stay in the convex hull of the foot support polygon, and to keep dynamic stability. And for each time instant, there was a support polygon active, and this constraint is just telling you that the ZMP should be inside the active support polygon at that moment. So this constraint with this cost function, we were finding the jerk, and then putting back into this equation, we were finding obtaining back the central mass trajectory and giving to the controller. So we have the user input that was setting desired velocity. There is a haptic planner that just it's running a higher frequency, like 250 Hz, and it's checking the touchdown whenever the touchdown is occurring, because it has a contact detection feature, and whenever a touchdown is occurring, it's starting the optimization. And in the optimization, it starts from the actual value of, tells the actual state of the robot in that moment. The optimization takes a while, let's say not much, like a few milliseconds. Provides back the trajectory of the COM. We need to, since the trajectory here is discretized at 40 milliseconds and not 4 milliseconds as required by this guy, then we have an interpolator that tries to match the different rates, and then the COM trajectory and the base orientation trajectory and the foot trajectory is given to the whole body controller. The whole body controller works out this is the inverse dynamics controller, what you call it this way, and is providing the desired torque that is given to the low-level controller that is trying to track the desired torque. Then this is what is changing. We have the reference velocity here. These are the predicted foothold, and at each step we replan. We're computing the future footholds, and we find out the ZMP trajectory and track it.
Meeting?
Yeah. 5 what?
5 minutes.
Okay. Yeah. So the extension is we want to get rid of the linear inverted pendulum model that allows us to just work on flat terrain and use the centroidal dynamics model. And this allows us to, as I said, have an anticipative behavior to pitch up the trunk, for example, whenever you want to step with the feet on a big step. This is a preliminary optimization which is linear. Let's say we linearize the model because now we are going to have, as Andrea taught you, the cross product term on the angular dynamic of the center of mass, the centroidal model. So this nonlinear term needs to be linearized if we want to write a linear problem. So this is a linear time variant problem, and we try to track the reference trajectory from the user in terms of speed in this case, and regularize the inputs that are, in this case, the contact forces, and enforcing the centroidal dynamics, unilaterality constraints, friction cones, and this tells which foot is on the ground and which foot is in the air. So I won't go in detail for this. I just want to tell you why we want to have models that are simple but descriptive enough. So if you look at the linear inverted pendulum assumptions, we also in the class, Andrea told you that there is an assumption that the terrain is flat, so the contact points are on the same plane. And there is also another strong assumption that the vertical velocity, this is a z, it should be, and the vertical acceleration should be zero, so the height is constant. There is no angular dynamics and there are no friction limits. So the linear inverted pendulum assumes infinite friction. And there are also no torque limits. While in the centroidal dynamic model, the basic assumption allows us to deal with multi-contact and non-coplanar fit contact, allows us to have vertical motion and angular motion, so we have a full dynamics for the linear, both the linear and angular case. And since we introduced the force variables, the contact force as input to the model, we can enforce friction limits, but still there are no torque limits. And the torque limits are very important when it comes to very complex situation like this, because in this case, in this robot, we have the torque profile. Since we have a piston, that is nonlinear torque profile, in this situation the torque drops significantly, and the robot reaches torque limits. So in addition to this, the centroidal model has no leg dynamics. So this means that the inertia tensor is constant, and we neglect the inertial effect due to the motion of the joints. So one idea was to incorporate the torque limits, but keep the dimension of the space where we plan trajectory small, because the centroidal dynamics model allows us to work in a six-dimensional space. That is the range space. But we want to make it more descriptive, and we need to find a way to describe the set of admissible contact forces that the robot can generate given its actuation capabilities. So if you have the torque limits, we can map them through the Jacobian. This mapping, I know, works in static condition because you will have the coupling due to the inertia matrix, but with this we neglect this because in our quadrature robot the inertia of the leg it's very small compared with the trunk, and this is different from humanoids. So this was licit kind of. Then we mapped into contact forces. So a box constraint in the torque space becomes like a polygon, which is called force polygon in the effector space. And these four polygons are time varying because the Jacobian depends on the configuration of the leg. So you have a different Jacobian in this point, you have a different Jacobian in this point, so the mapping is affected the torque into the force. And then with the Minkowski sum, we can sum these polygons that are polytopes together and find a 6D representation, polytope representation that tells what are the admissible branches, what are the admissible accelerations that the robot can have at this COM, considering that is respecting actuation limits. So it's a way to map the actuation limit for the joints from the joint space to a 6D space, and this allows us to write constraints for CM accelerations and solve the optimization problem in a 6-dimensional space and finding CM trajectories that are feasible in terms of actuation. The other idea is to use a feasible region. So find a convex region where you can put, the robot can put its COM in order to be statically stable, compensate gravity, and satisfy friction and actuation constraints. And we see that this region can be very different according to the normal contour of the contact. If the contact are like this, the feasible region is this. If the contact normal is like this, then it's even outside the convex hull of the polygon. So it really depends. In the linear vector pendulum, is always the convex hull of the polygon. So now we have a problem. How can we do? I have still 20 slides. 15. 15.
I don't think that's legal. At the very least, you need to take a break.
No, let's take a break and we continue.
Or maybe we can schedule a second seminar.
We can schedule a second seminar. Yeah, I mean, I finished this. This part and the transparent part.
I would just finish this part.
Yeah. Okay. And so this the office. By the way, these topics I will talk about in another seminar because it's very big. So I put just 2 slides. What I wanted to give you as a take-home message is that this region is dependent on the normals and on the friction coefficient and also on the external load and torque limits. So if you load the robot, the region where you can put your COM and equilibrate, given an actuation limit, becomes smaller. And this is very useful for planning. We can use this region for planning trajectories. And it's only 2D and it's very fast to compute. We managed to compute this region at 50 Hz online. And we did the experiment with the real robot. As I said, this will be part of the and that's it. Also this part will be because it's a bit there are many things I had to choose between all the topics, but still it's can I just show you the video of Real?
Just show the video.
Yeah. So this is an experiment we did with a new robot that was pulling an airplane of 3 tons. We had to overcome friction. At the beginning, we had to be able to apply 800 Newton peak force, in this rope, and then start working. And the way it's working, it's what we call transparent locomotion. So the first the base is moving, and then the feet follow to keep stability, which is actually the dual approach of what we did so far, which was moving first the feet and then follow with the base. So that's it.
I know it's late, but are there questions?
Go ahead. No, go ahead. I don't have an actual question, just something I was thinking about when we were showing the video of the quadruped that was working. And I was thinking of just, these kind of approaches that are bio-inspired. Usually you pretend to replicate in some sense how actually the biomechanics of animals, for in this case, is working. So I was simply thinking about this kind of limit that seems to be in this actual implementation, in which you try to keep the equilibrium using this sort of dynamic stability when you're just standing still somewhere, while this is something that an actual animal wouldn't do. So I was simply thinking, and maybe you can have some hint on this point, how, what are the actual, I don't know if sensing capabilities or intelligence or whatever that is still missing in this kind of approaches to actually replicate what's going on in an actual animal that is walking on 4 legs.
Correct. First, an animal is mammal is different from a robot because it's made of flesh, not from aluminum alloy,
Yeah.
and so actually it's not perfectly rigid, and it has sensors all over the leg. It has, for example, in the foot, it has a skin, and the skin it can be used for touching, for detecting the exact central pressure location. So, or the skin can be used to check wherever the external disturbance is coming, because we can only estimate, for example, external disturbance in the effect of the external disturbance, but we cannot find the location exactly. So, in terms of locomotion, it's still an open question how animals work and move. There are biomechanics studies that we read papers from, like cheetah running, and we see the ground action force profile. So we try, for example, to emulate the profile of ground direction forces that has some bell shape or kind of like this while walking, and this can be, for example, emulated with a slip, which means springy linear inverted pendulum, which is like an inverted pendulum with a spring. So it's really difficult to understand. These are open research questions. What we try to do is we try to, given the kinematics we have and the dynamics we have, so we have still a rigid robot, so we try to do the best that we can do given the platform. So we kind of take inspiration from the nature, but we need to tailor this inspiration to the real platform. So in our case, for example, there are people that take exactly opposite approach. They create a soft robot, for example. In our case, we try to make the robot rigid in order to be able to estimate appropriately the foot location. So we try to remove compliance from the leg, because whatever you cannot measure, you need to model, and if you don't model, it's unpredictable. It's noise, and so it's difficult. It's difficult to reply. There are two philosophies, let's say. There are people that just don't care. They just I don't know, take a soft robot and do some heuristics that tells you, I don't know, jump. Okay, I need to push harder to jump. Last time you jumped 45 centimeters, you need to jump 50, so you need to push a little bit harder. But since we are using the model of the robot, we try, we have a machine that we can model, we want to exploit it. So we try to identify the model. We have let's say a classical approach in this sense. But I agree that the humans, animals, they have the feedback. It's very low. The feedback rate is 100 milliseconds from the nervous system to the brain. So another approach that we use, for example, is in the trot. It's exactly taking this direction. Is central pattern generator (CPG), which is so if we have in humans, we have on the spinal cord, we have these oscillators, and the brain just give high-level commands like step height, length, step height, and this oscillator they drive the working motion. So we implemented this for the trot, for example, and we just this oscillator that are synchronized and between legs, and we can change the step height or the step length. Changing the ellipse of the oscillation. So this is a kind of by inspiration. It was working for us quite good.
Thank you.
Okay. Any other question?
I'll save mine for later.
Okay. So we can all thank Michele again.
Yeah.